we just talked about the Smith chart applied to searching for the input impedance and also the standing wave ratio, signal maxima, minima, and so on. But in fact, a Smith chart is quite powerful. It can also be used to look for the admittance of a circuit. And the definition of the admittance is given by inverse of the impedance. Mathematically, you can write it like this. So the admittance Y is equal to 1 over Z. And again, you could have the real part and also imaginary part associated with this admittance. And this admittance is particularly useful when you deal with parallel circuit, because for parallel circuit, the total admittance of this parallel circuit is just the sum of Y1 plus Y2, the sum of individual admittances. And so sometimes we want to use admittance in studying transmission line instead of using the impedance. And again, a chart should be created as a tool for all kinds of the transmission line with different characteristic impedance. So we define normalized admittance as the admittance divided by the characteristic admittance. And this characteristic admittance is equal to the inverse of the characteristic impedance. And again, you have the real part and imaginary part associated with it. And the normalized admittance turned out to be just the inverse of the normalized impedance. And if you still remember this, the normalized low impedance is equal to the low impedance, which is the VL divided by IL, and then divide the whole thing with the characteristic impedance. And this ZL, the normalized impedance, is given by this expression, 1 plus gamma divided by 1 minus gamma. And if you do the same calculation for the normalized admittance, then you end up having this expression. And on the numerator, you have the 1 minus gamma, and the denominator is 1 plus gamma. And you notice that the only difference between these two expressions is that you flip the plus sign and minus sign here to create the same expression. So now we have a normalized low admittance like this, and compare with the normalized low impedance, you have this sign reversal on these two expressions. And so if you want to convert this expression to this exactly, then what you can do is that you move the gamma value on the Smith chart by angle equal to pi. So if you just move on your transmission line by a quarter wavelength, then you will have this additional phase attached to this gamma value. And then you end up having an expression exactly the same as this one. So this means that given a low point on the Smith chart, if you just move toward the generator by 180 degrees, then the value of the YL can be read from this Smith chart, because you create the same expressions for the impedance and the admittance. So this is the way you find the corresponding admittance values from a given impedance value. Now, let me give you one example. For example, I want to know the input admittance at this point, subject to low impedance at the end equal to 2 minus GA. And again, 2 minus GA is the normalized low impedance. And we want to find out what the YI, the input admittance is. And so previously we already locate this low impedance point, which is right here, A, and then you can create a standing wave ratio circle with a radius equal to OA. And now we want to find the input impedance at this location. And previously, we also found that the input impedance can be read from this point B by rotating this line toward the generator by a length equal to 0.1 wavelengths, because this location is the 0.1 wavelengths from the end of the transmission line. So you can read the input impedance at B, and if you want to convert the input impedance at B into admittance, then you continue to rotate this line by additional 180 degrees. And then you will be intercepting this line with SWR circle at this point. And now you will be ready to read the admittance, the normalized admittance at this point. And this can be the rate to be 0.72 plus 0.82 GA. So this is how you find the normalized admittance subject to a low impedance. But first you have to do impedance transformation to determine the input impedance at this point, and then rotate this line by additional 180 degrees, and then you read the values for RL and XL, and those values in fact are the admittance values. So this is how you find the input admittance. So in this session, I teach you the admittance, which is just the inverse of the impedance. And this admittance value is going to be quite useful when you deal with parallel circuit, because the total admittance of a parallel circuit is just the sum of individual admittances. And on the Smith chart, if you want to read the admittance of some impedance value, then you first find out the location of the impedance, and then rotate the value on the SWR circle by 180 degrees. Then you'll be able to read the values of the admittance. So this is a few points you want to remember in this session. Thank you.